Okay, in this video we're going to look at the beginning of Chapter 1 and cover some of that material. Chapter 1 deals with patterns of motion, that is the basic ideas and concepts of motion, as well as the concept of equilibrium, and that'll be in terms of forces, as we'll see later. In this lecture specifically, we're going to be looking at Aristotle's ideas about motion, Galileo's concept of inertia, and then we're going to define the concept of mass, which is actually a measurement of inertia. Okay, so we're going to be looking at Aristotle's views on motion. Now, Aristotle is, of course, very famous as a philosopher. He's most famous for his work on philosophy, but he was also a great scientist. If you've ever taken a course on introductory biology, you probably learned that Aristotle is considered the father of modern biology. He's the guy who basically invented the science of biology as we know it today. Now, Aristotle also did a lot of work on physics, but unfortunately, most of his ideas about physics turned out to simply be wrong. A big reason for that is Aristotle didn't really have all the tools that he needed to be able to do proper physics experiments. For example, the clock had not been invented yet. He didn't have a way of accurately measuring time. So if you want to talk about measuring motion, the way things move in space and time, you can't really do that very well if you don't have a way of measuring time. So Aristotle, instead of doing experiment, he just thought about things, and he came up with some relatively reasonable conclusions, but they just happened to be wrong. Now, when Aristotle talked about motion, he classified motion into two different types, what he called natural motion and what he called violent motion. When Aristotle talked about natural motion, he referred to objects that moved naturally, things that didn't require some sort of external force to move. And so an example of this would be a book lying at rest on a table naturally remains at rest. If you let go of a book, it naturally falls towards the earth. Fire, the embers from fire, they naturally rise up. That's their natural motion, according to Aristotle. You know, the sun rising and setting, that was sort of an idea that he had of a natural motion. So he had the idea that some things just move naturally on their own, and then other things required forces to make them move. So in Aristotle's view, and again, this is not a true view, it's not a correct view, but this is what his theory was. In his view, things that did require some sort of external force to keep them moving, he called that violent motion. And so examples of this would be pushing a book along a table. The book's not going to move unless you push it. Lifting a book off of a table. A book's not going to simply fly off of a table on its own. You have to pick it up and lift it off the table. So he considered those ideas of violent motion. And the word violent doesn't really mean what we normally think of as violent, but it was just the words that he used to describe that kind of motion. Now, the person who finally proved that Aristotle's ideas were wrong was a guy named Galileo. His actual name was Galileo Galilei, but we just call him Galileo. We call him by his first name. And he introduced an idea that we now call inertia. And his ideas were very, very different from those of Aristotle's. What Galileo said was that in the absence of some sort of force, once an object is moving, it will continue moving indefinitely. Now, that seems kind of wrong, and Aristotle seems kind of right, but it turns out to be backwards. If you push a book across a table and let it slide across the table, once you stop pushing it, it's going to slide for a bit and it'll slow down and stop. And Aristotle would have said, well, that's because the book's natural state is to be at rest. That's its natural motion. But what Galileo realized was that there's more forces acting on the book than just the pushing force of you pushing it. There's also air resistance. There's friction between the book and the table. And so when you stop pushing the book, these other forces are the ones that are dominating the motion of the book, and they're the ones that slow it down. And he actually did experiments where he rolled balls down these ramps that he built and let them go forward. And he had these balls rolling down these grooves. And what he did was he polished the grooves to make them have less friction. And he found that when he did that, the balls rolled further and further. And the less friction he created in the system, the further the balls would roll. And so he had the idea that if he could completely eliminate friction, that the ball would keep going forever as long as the track was straight and kept going. And it turns out that Galileo was right. Things tend to want to keep whatever motion they have. That's what inertia means. An object wants to maintain its state of motion. If it's sitting at rest, it wants to stay sitting at rest. If you want to change its motion, you have to apply a force. So if it's sitting at rest and you want to move it, you got to apply a force. But if it's already moving, it wants to keep the motion it has. So if you want to slow it down or speed it up or make it move in a different direction, you have to apply a force in that situation too. Now I want to talk in this slide about something that Aristotle also got wrong. Aristotle said that heavier objects will tend to fall faster than lighter objects. If you have a baseball and a bowling ball and you drop them from the same height at the same time, Aristotle said that the bowling ball should hit the ground first because it's being pulled down harder by its weight being heavier. But Galileo actually did experiments. He rolled balls of different masses down his inclined planes, down his ramps, and he dropped balls from different heights, and he found out that regardless of how heavy or massive a ball is or how light a ball is, if you drop two balls from the same height and you release them at the same time, they always hit the ground at the same time. Now that's not an obvious result, but what he did was he did experiments. And experiments are how we learn things in science. And so this experiment's been repeated millions and millions of times. And so we're pretty darn confident that Galileo was actually right. That if you take things and you drop them and they have the same mass or different masses, it doesn't matter. They're going to hit the ground at the same time. The only exception to this is if you drop something that is very, very light and has a very large area so that the wind resistance can affect its motion. If you drop two heavy objects that are, small, the air resistance is not going to be that much of an effect, and so you can expect them to hit the ground at the same time. Now, you could take something like a styrofoam peanut and something like a rock and drop them. The rock's probably going to hit the ground first because the air resistance is enough to affect the motion of the styrofoam peanut. But you can actually build a chamber where you suck out all the air. And if you drop them from the same height at the same time and there's no air resistance to affect the motion, boom, they hit at the same time, every time. Now, if we go back to Galileo's concept of inertia, remember, inertia is that idea that things want to keep whatever motion they have. If you have something moving horizontally, you don't have to have some external force to keep it moving as long as there's no friction or no other forces slowing it down. Now this slide is showing another thing that Galileo experimented with. And he built these ramps, and you can see the idea here is in this first ramp here, there's a very small horizontal path. And in the second ramp here, there's a longer horizontal path, and there's a different angle. But no matter the length of the path or the angles, as long as the ball didn't have a lot of friction, it would always roll down the inclined plane, roll along the path, and then roll up the other ramp, and it would generally go back to its height. And so each of these are showing that the ball wants to return to the same height it had. Now, what Galileo imagined was that if you kept this going forever and ever, it can't get back up to its height. So that was another thing that led him to this idea that if you let the ball go, it's going to keep going forever. Again, provided there's no friction or some other force to slow it down. So here we have sort of a formal definition of the concept of inertia. Inertia is the tendency of a moving body to keep moving. The main idea here is that every material object resists change. That's the key word. Inertia tells us that things want to resist a change in its state of motion. That's the property of inertia. Now, this slide has a little bit of a review quiz, and so which of the bullet points is correct? The use of inclined planes for Galileo's experiment helped him to eliminate the acceleration of free fall, discover the concept of energy, discover the property called inertia, or discover the concept of momentum. Well, obviously, we've been talking about inertia, so that is going to be the answer. And we can see that in this slide, where the discover the property called inertia is highlighted. And we have an explanation here. We can note that inertia is a property of matter. It's not a reason for the behavior of matter. And so inertia is something that's built into matter. All matter has the property of inertia. Now, what we find out from experiment is that some objects have more inertia than other objects. And we call the measure of a body's inertia its mass. And so it turns out that the amount of inertia that a body possesses depends on how much matter is present in that body. The more matter something has, the more inertia it has, and the bigger its mass. So here we have a new definition for you, the definition of mass. Mass is a measure of a body's inertia, and it's related to the quantity of matter contained in that object. Now, another concept that's related to mass is the concept of weight. Weight is a measure of the amount of the gravitational pull on an object. That is, for example, the Earth's gravity is pulling you down onto it, and you have a certain weight. But you also have a certain mass because your body is made up of matter. And the amount of weight you have depends on how much mass you have. The more mass you have, the more you're going to weigh. But they're not the same thing. Because if you were to go to the moon's gravity is weaker than the Earth's gravity. So you would actually weigh less on the moon, but you would have the same amount of matter in your body, unless you cut off your arm or something. So again, that's a very important distinction. Mass is a measure of your body's inertia, and it's related to how much matter you have in your body. Your weight is a measure of how much force gravity is pulling on you with. Now, another concept that's important is the idea of volume. So we've already talked about mass, and we know that mass is related to how much matter an object contains. Volume involves how much space that object occupies. So you have an object that has a certain amount of matter. That amount of matter takes up a certain amount of space, and that's the volume that object occupies. Now, we can look at this concept of inertia, and this is a review quiz again. So which of the following the concept of inertia mostly involves? Mass, weight, volume, or density? And the answer is, of course, mass. That inertia is a measure of an object's mass. So here you can see the correct answer highlighted. The concept of inertia mostly involves mass. Okay, so in this slide we're talking about mass, and we are going to define the unit of mass. Now this is the metric system unit of mass. It's known as the kilogram. And mass, as we've said, is related to weight. And so on the Earth's surface, 1 kilogram of material weighs 10 newtons. It actually weighs 9.81 newtons, but it's about 10 newtons. So that's a good rule of thumb, that 1 kilogram weighs 10 newtons. Now what in the heck is a newton? A newton is just a unit of force, or a unit of weight, like pounds. 1 kilogram weighs about 2.2 pounds. And so if I tell you that, you kind of know what 2.2 pounds weighs. Well, it also weighs 10 newtons. And that's kind of like saying you could measure a distance in miles, or you could measure a distance in kilometers. The number in front of the unit would be different, but it's the same distance. So here, 10 newtons is about 2.2 pounds. And why do we call it a Newton? Well, that's the metric system unit for force. That's the reason. So in science, we always deal with the metric system because it's easier to use for scientific calculations. And so around the world, even in the United States, the metric system is what's used in science. Now, if you want to have a better idea of how much a Newton weighs, to have sort of a sense of it, you might remember the famous story about Isaac Newton. That's who the Newton unit is named for. The story says that an apple fell on his head and he discovered gravity. You might have learned that in grade school. Well, a medium-sized apple weighs about a Newton. Coincidentally, the original iPhone also weighed about a Newton. So, Newtons and apples, they seem tied together somehow. Now, here's an illustration of a famous experiment. If you hang a weight from the ceiling and you have a string also underneath and you tug on the string and you pull until one of the strings breaks, which string is going to break first? It turns out it depends on whether or not you pull the string slowly or if you jerk the string. If you pull the string slowly, the top spring breaks. If you jerk on it, then the bottom string is the one that tends to break. And so why is that? Well, let's consider the first case where we're pulling the string slowly and the top string breaks. What is that going to illustrate? It's actually illustrating the weight of the ball, because the weight of the ball is pulling on that top string. And then you're pulling slowly on that top string and you're adding to the tension on the top string until it breaks. So we can see the answer highlighted here that the top string breaks because of the weight of the ball. And the explanation is that the tension in the top string is the pulling tension plus the weight of the ball, both which act to break the top string. Now, what about in the other situation where you pull on the string really quickly, you jerk it? In that situation, we said the bottom string tends to break. So what is that an illustration of? Well, it's not an illustration of the weight of the ball. It's actually an illustration of the mass of the ball. So how is that the case? How is it an illustration of the mass of the ball? Well, remember what the mass of an object is. It's a measure of its inertia. It's wanting to keep its position, its motion intact. And so this mass here, it wants to stay where it is. And so if you jerk on the bottom string, you're going up against its inertia. And you have to overcome its inertia to get it to move. And so it wants to stay where it is, so all of that tension goes into the bottom string. Okay, the last concept that we're going to cover in this video is the concept of density. And density is the measure of how much mass occupies a given space. And there's actually a formula for it, or an equation. The equation is that the density of the object is equal to its mass divided by its volume. And so, of course, mass is how much matter is in the object, and volume is how much space the object takes up. And the units are generally going to be something like grams per cubic centimeter or kilograms per cubic meter. These are metric system units that are very common for density. And again, that's just mass divided by volume. So here is a slide with another concept review quiz. So the density of 1 kilogram of iron is going to be less on the moon, the same on the moon, greater on the moon, or all of the above. Well, obviously it can't be both less and greater, so all of the above can't be the right answer. And it turns out that the answer is going to be that the density of 1 kilogram of iron is the same on the moon as it is on the Earth or Jupiter or anywhere else. Because remember, mass is how much matter is present in the body, and volume is how much space the body takes up. So if you were to teleport to the moon, you're not going to lose any mass. You're going to, have all your arms and your legs and all the rest of you. It's going to have the same amount of matter, and the amount of space that you take up is going to be the same too. So your density won't change. So that's it for this lecture. We'll continue on with the next lecture as we go.